the August paper, we'll have a look at the first question. Our vessel's alongside in salt water with a list of 4 degrees to port. We're nearing completion of cargo and we're given a displacement and a GM, and with 3 parcels of cargo to load, and we're asked initially which parcel of cargo should be loaded into each of the available locations so that the vessel completes upright with an improved GM. So dealing with the upright first, what we need to do is get rid of our initial listing moments. So the first thing you would have to do really is calculate the initial listing moments. So we multiply obviously displacement times angle times GM, and we find we've got 106 tonnemeters to port. So what you need to do, or what you could do with this one, is really a process of elimination. You can multiply a weight by its distance from the centre line and see which the product of 2 give you 106 tonnemeters to starboard. The way I approached it, just because I suppose we all think differently, I thought, well, the bigger the weight, the smaller the kg. Because I looked at it initially to do with the GM, I thought, well, if I place the bigger weights, 19 tons, lower down near the keel, and the smaller weight higher up, that would mean that our final kg would be less than our initial kg, and of course that would improve the GM. And coincidentally, when I'd done that, I then started looking at the figures and thinking, okay, well, I've put that in that position, therefore I've created these moments, and it worked out at 106, so I knew I'd got the right answer. So you could have approached it from 2 different ways. Just curiously, if you'd gone in the tables to get the final KM, because of course our displacement changes, actually our final GM was less than our initial GM. But I guess looking at the question, it just asks us for an improved GM, and I just take it to mean, well, our kg is definitely reduced, therefore our centre of gravity has got better. But it is a bit of an anomaly, I think, in this question, maybe. Part B, whether the ship on completion of loading complies with the minimum criteria. Well, you go into the maximum kg tables with the displacement, interpolation, and I found that the vessel complies, but only just. So, as I like to stipulate here, these are just my own workings, my own reading of the questions. I don't get any answers, it's just what I think the answers to the question are. So let's look at the second one. This is a typical fluid GM angle of lull question. It hasn't come up for quite a while, where with a midship rectangular deck, and it's filled with dock water, and the height of the deck above the keel 12.15. Where it's been slightly different than previous ones, we're in dock water rather than salt water. So let's work through the problem. So first of all, I worked out the weight of water on deck, and then I got the kg of the water on deck, and the kg is from the keel to the centre of the weight. So we're told that our deck is 12.15, the depth of water on deck is 0.6, so our kg must be from here to here, which is 12.45. Free surface moments, lb cubed over 12, times density gives 22,956. Now what you had to do, of course, is go in the tables and get the underwater volume of the vessel at 8.74. In other words, use the freshwater column, which is the underwater volume at those drafts. Then multiply it by the density, and we've got our initial displacement. Given the kg, there's the weight that we've loaded, free surface moments, fluid kg, then obviously with your final displacement, you must divide that by the density, and that will give you your underwater volume. Go into the tables and get the km and the kb at the same time, and we find that the fluid GM, by my workings, is minus 0.6. Now with these problems you always have to get a minus GM, because if you don't get a minus GM you're not going to get an angle of lull. So our BM is Km minus Kb, 8.47 minus 4.67, and then using the angle of lull formula, tan theta square root of minus 2 times GM over BM, you get an angle of 10.1 degrees, an angle of lull. And obviously the minus GM and the minus 2 cancel each other to enable us to actually use that formula. So just my own interpretation, I get 10.1 degrees as the answer to the second part. Okay, question 3. We're in salt water, we're given our drafts, and we're going to proceed on a short coastal passage, and we're going to consume the various weights, and the after peak was fully deballasted for salt water, and we have to calculate the minimum clearance over the shoal with a predicted depth of 9.6 and the minimum clearance if the vessel is brought to an even keel. So again, just my own workings. Get our initial true mean draft, the usual procedure. From the tables using that, get your displacement MCTC LCB, then use the formula trim equals displacement times LCB difference LCG over MCTC, not forgetting to put your trim in centimetres, very important, and we get our initial LCG. Then I've worked out the weight in the after perpendicular, obviously multiplying the value by 1.025, the volume, and it gives you 110.7 at 3.07. So I've then listed all the weights, as you can see here, taken them off, and got a final LCG. Go up into the tables again with the displacement and get your true mean draft, MCTC, LCB, LCF. Use again the formula, the trim formula, displacement times LCB difference LCG over MCTC, and we get trim of 28.3 centimetres. Then use the change of trim formula to apportion the trim forward and aft, as I've done here. The vessel is trimmed by the stern, so we add the after value, subtract the forward value. Again, just my own interpretation. My minimum clearance is 9.6 minus the deeper draft, 1.326. And the minimum even keel clearance, well, it would be the draft that we got here, 8.138, minus the 9.6, and I get 1.462. So that's just my own workings of the August paper.